This lecture looks at neural networks. It's going to start with an introduction in neural networks, and the following lecture will then look at specific learning algorithms and architectures for neural networks. So basically, your neural network takes analogy from how the brain works. Your neural network is essentially a mathematical model of the way the neurons are connected to form a network for passing and accepting signals to perform different functions. What neural networks bring that the other techniques don't bring is the whole idea of parallel processing. So whereas the algorithms we looked at previously do things sequentially, neural networks actually do them in parallel. There have been software implementations of neural networks and hardware implementations. We'll be focusing on software implementations. The whole idea behind hardware implementations is to try and move away from doing things sequentially the way our traditional machines do it, and to actually do things in parallel to speed up processing and to reduce processing time. Since the inception of neural networks, there have been a number of different neural network architectures and different learning algorithms, and this is the main way in which the neural networks differ, basically based on the architecture of the neural network and the algorithm used to train the neural network. So your learning algorithms are essentially used to train the neural network. If we look at a biological neuron, the way the biological neuron works is you have dendrites. The purpose of those dendrites are to accept inputs. Those inputs come from other other neurons that the neuron is connected to in the neural network. Once those inputs are input via the dendrites, they're processed in some way, and that processing happens in the cell body. Once the processing happens, the neuron will then fire or not fire. Now, what we mean by fire or not fire is it'll either produce an output signal or it won't produce an output signal. The deciding factor as to whether it will produce an output signal or not happens when it's transmitted along the axon. So when it's transmitted along the axon, a decision is made as to whether it will fire or not. If it does fire and a signal is output, that signal is then transferred over the synapse to another neuron. So how do we now implement this in a computational neuron? We basically use the same idea. So the P that you see in the diagram is your set of input values. Those input values correspond to the inputs that were input via the dendrite in the biological neuron. Those values that you get are then multiplied by weights, and that's what the W vector represents. So W represents a set of weights. So if your inputs are 1 to n, W will be 1 to n. And in some neural network architectures, we have something called a bias, and that's represented by B in the diagram. A bias always has an input value of 1, and the purpose of the bias is to have some impact on your activation function, either moving it to the left or the right. So the processing that happened in the cell body in your biological neuron, that's achieved by taking a weighted sum of the inputs, so W1 through Wn multiplied by P1 through Pn, and adding the bias. That sum that you get is represented by the value n, and this is equivalent to what was transmitted along the axon. So the value n is then input into an activation function, and that's represented by f. And that activation function then determines whether that neuron is going to fire or not. So your activation functions can be something as simple as a binary step function, or more complicated like a sigmoid function. And that n value will then either produce a value of 0 or 1 or some output for the neural network. So in its simplest form, your activation function will cause your neuron to fire or not, and that's equivalent to a 1 or 0. But you can get different outputs, and that will also be application dependent and learning algorithm dependent. So the whole idea of working out what W is and what B is, that's what happens during the training process. And that's usually what you need to use a learning algorithm for. So just to summarize what happens in your computational neural network and how this takes an analogy from your biological neural network. So each neuron, there's some processing that happens, and that's equivalent to the processing that happened along the cell body. In the case of the computational neuron, that processing is basically the sum of each input multiplied by the corresponding weight found by the learning algorithm, and the bias is added onto that. So what are these weights and biases, and how do we determine them? So the weights and biases are the things that we actually determine during training. In yesterday's lecture, we spoke about the whole idea of supervised learning, and all supervised learning techniques, machine learning techniques, go through a process of training and then a process of testing. So when it comes to neural networks, the training is actually identifying what the weight should be and what the bias should be based on the training set that has been provided. So those inputs that we spoke about that come across the dendrites and were equivalent to the vector P, those inputs are actually provided from the training set. So how do we do training? We need learning algorithms to actually do the training, and those learning algorithms determine what the weights are and what the bias is. And the input for those learning algorithms are essentially your training set. So once you've actually inputted your input values and you've multiplied it by the weights and added the bias, in order for that neuron to produce an activation, you need an activation function. There are different activation functions. Usually different learning algorithms use different activation functions, and sometimes the activation function may be problem dependent. So once you've trained your neural network, that means you've got your set of weights and you've got your biases for the neural network. The idea is to see whether it generalizes well. And like all machine learning techniques with supervised learning, you need to test the neural network. So when you test the neural network, one of two things could happen. You could find it generalizes well, or it's not generalizing well. The initial training resulted in overfitting. If that happens, you've got to go back and retrain. And the things that you can change are things like the parameter values for your training algorithms. Like genetic algorithms, training algorithms also have parameter values which you'd have to tune. Alternatively, your training set may not have been effective enough, and you've got to go back and reconstruct your training set to allow your neural network that you produced, or those weights and biases that you produce, allow the neural network to generalize better. So far, we've looked at a single neuron, but a single neuron cannot do much. It's not very powerful. You usually need a network of neurons in order to achieve anything. So what we're going to look at now are different types of architectures, different types of neural network architectures. So this we've seen already. You've got a single layer, and that layer consists of just one neuron. The neuron has a number of inputs. It has multiple inputs, and those range from 1 to R in this case. If we look at this architecture, it's slightly different. Again, you've got one layer, but instead of the layer having just one neuron, there are now S neurons in this layer. In this example, there are two layers in your neural network. The first layer has two neurons, and the second layer has one neuron. So that's W3 and W1 and 2, neuron 1 and 2 form the first part. It has weights W1 and weights W2. And the third neuron, neuron 3, has weights that begin with W3 to indicate that those weights are for the third neuron. This neural network is a classic example of a multi-layer neural network. Here there are 3 layers, and each layer is composed of S neurons. If you think of convolutional neural networks, they have many, many more layers. They have hundreds of layers. And that is what makes them so good at image processing. They usually map pixels to the different neurons, from the inputs to the different neurons. So this is an example of a classical neural network where the number of layers can actually grow in that neural network. The next thing that we're going to do a quick overview of is what's happened since the inception of neural networks, and where are we now in terms of different learning algorithms and architectures that have come up. So the first neuron that was developed at the inception of neural networks is something called the McCulloch-Pitts neuron. We are going to look at that in this lecture just to get an idea of what the first neuron was, how simple it was, and how things have changed since then, and how neural networks have become more complex in architecture. And the first learning rule that came up was something called Hebbian learning, and we will look at it when we look at perceptual learning algorithms, an alternative to the learning done in the learning algorithm. As time went by, the next group of algorithms or group of architectures and algorithms were the perceptrons and the Adelane neural networks. And then the different types of architectures and learning algorithms came up and were named by different research. For example, the Cohen neural network, the Anderson neural network, etc. And as we progressed, the whole idea of recurrent neural networks was then initiated, and the Hopfield neural network is an example of a recurrent neural network. The backpropagation is a gradient descent algorithm that is a very popular algorithm and is quite effective. So that's one of the algorithms that we're going to look at. And then in the 90s, recurrent neural networks were emphasized, and the whole idea of gradient-based learning. LSTMs are very powerful recurrent neural networks that are used a lot in real-world applications, from finance to image processing, and the whole idea of gradient-based learning was reinforced. And currently, as you know, deep learning and convolutional neural networks, there's lots of a hype about that, there's a buzz about that, and they are very, very effective when it comes to image processing, whether it's medical images, whether it's biological images, etc. So as I mentioned, the first neuron that was developed was something called the McCulloch-Pitts neuron. And as you'll see, it's a very, very simple architecture, and that's what's so surprising. This was the first neuron that was developed, you could have a network of these neurons. But as you see, if you compare it to what we work with in this day and age, where we have very complex neural networks, it's surprising that such a simple neural network was effective in certain domains when it came about. So this was the first neuron. It basically takes binary inputs and produces binary outputs. The activation function is a very simple activation function. It's a step function. So it will output a 1 if the sum of the weights and the inputs is greater than and equal to a theta value, and 0 if it's less than the theta value. So you'll notice I've mentioned just the sum of the inputs and the weights and no bias. This neural network doesn't have a bias included in its architecture. I'm sure you're also wondering, what is the value theta? Like I said, certain learning algorithms have parameter values, and when it comes to the McCulloch-Pitts learning algorithm, theta is a parameter value. It's something that you'd have to tune when you're designing the neuron and the neural network, in a similar way that you tuned the population size and the number of generations for your genetic algorithm. This is a very simple example of a McCulloch-Pitts neuron. So if you look at the example, it has 3 inputs, x1, x2, and x3. This is a trained neuron. As you can see, its weights have already been determined. So it has W1 has a value of 2, W2 a value of 2, and W3 a value of 1, and it has a single output. So the sum of that will be applied to, will be input to the activation function F, and depending on what that value is compared to the theta value, your neuron will fire or not fire. Excuse me. So suppose you were now required to design a McCulloch-Pitts neuron for the OR function. So one of the things neural networks can do is emulate a function. If you look at the OR function, it basically has 2 inputs. It has a value x1 and a value x2, and then a corresponding output. So if both the input values are 0, its output value is also 0. But if either of the input values are 1, then the output value is also 1. And similarly, if both the input values are 1, then the output value is 1. So if you had to design a McCulloch-Pitts neuron to emulate this function, what would it involve? Basically, you have to determine what the weights are, and you've got to determine the theta value. So I'll give you a minute just to think about it. What do you think would be the appropriate weights, and what would be an appropriate theta value to get the target values given the particular input values? So the set that we're looking at now, you can think of as a training set, and it's a training set to produce a neural network that can actually emulate the OR function. One particular combination that will work is if you took W1 to be 2, W2 to be 2, and theta to be 2 as well. So if we look at the first data instance of the training set, you've got 0 times 2 plus 0 times 2, which will give you 0. 0 is not greater than theta, so your neuron won't fire. Your activation function will give you a value of 0. Similarly, if you look at the next data instance, x1 is 0, so it's 0 times 2 plus 1 times 2, which will give you a value of 2. If you apply the activation function to this is going to give you an output value of 1. The third data instance, same thing. Here you've got x1 equal to 1, so it's 1 times 2 plus 0 times 2, which will give you an n value of 2. And once you apply the activation, this 2 is equal to theta, so you get an output of 1. And lastly, both your input values are 1, so that's 1 times 2 plus 1 times 2, which is going to give you an n value of 4. And if you apply the activation function, 4 is greater than theta, so you're going to get an output of 1. So we've now manually trained the neural network. It was a very simple architecture, just a single neuron, so we were able to do this. But usually you have a network of neurons and you need weights for each of the inputs going into those neurons, and a learning algorithm is what you'd use to do that. The last section that we're going to look at is linear separability. Why linear separability is important is that it actually helps you determine how many layers your neural network needs. So basically, you can use linear separability to decide whether you're going to use a single layered neural network or whether you need a multi-layer neural network. So suppose you're required to train a McCulloch-Pitts neuron to perform the XOR logical function. So just remember the XOR is the exclusive OR function. It's the same as the OR function, with the only difference being that when you have both inputs being the same, that is x1 and x2 either being 0 or x1 and x2 either being 1, then the output will be 0. However, if you have x1 1 and x2 0 or x2 1 and x1 0, then your output will be 1. So I'm going to give you a minute or so to think about it. If you had to actually represent or get your McCulloch-Pitts neuron to emulate an XOR function, what would the weights be and what would the theta value be? Have you come up with an answers yet? So even if it took longer than the time that I've given you, you would not be able to solve the problem. The reason being is that the XOR function is not linear separable. So if a problem is not linear separable, you cannot actually solve it using a single layer neural network. You need more than one layer of your neural network. So just to have a look at what we mean by linear separability, if you look at the graph on the left-hand side, the OR graph, basically what the graphs are plotting is where the neuron will fire compared to where the neuron will not fire. So if you look at the OR function, in order to see this more clearly, the 0 is replaced by a -1. So wherever you would have a value of 0, this is -1. So if x1 is 1 and x2 is 0 or -1, your neuron's going to fire. If x2 is 0, if x2 is 1 and x1 is 0 or -1, your neuron's going to fire. So there's a plus in that quadrant. Similarly, if both x1 and x2 are 1 for the OR function, your neuron's going to fire. So there's a plus. But in the case where both x1 and x2 are -1, your neuron doesn't fire and you've got a value of -1. Now you can see you can clearly divide the region where the neuron's going to fire from the region where the neuron's not going to fire with the line going through the points for the OR function. If you look at the XOR function, the two quadrants where the neuron will fire are the cases where x1 is -1 and x2 is 1, and similarly where x1 is 1 and x2 is -1, which is representing the 0. The two cases where the neuron won't fire is whenever both x1 and x2 have the same value. So if x1 is 1 and x2 is 1, there's a minus indicating the neuron won't fire. And similarly, when x1 is -1 and x2 is -1, it also won't fire. Now, if you look at the graph for XO, you can see that you cannot actually divide the area where the neuron will fire from where the neuron will not fire by a single line. And this basically means that the function is not linearly separable. Because the function is not linearly separable, you're going to need more than one layer in your neural network to solve the problem, so you need a multi-layer neural network. So the main aim of this lecture was to just provide an introduction to neural networks. What we're going to start looking at now are the learning algorithms in more detail and the different architectures in more detail. So the next architecture that we're going to look at is the perceptron architecture, and we're going to look at the perceptron learning algorithm. And that we'll do in the next lecture.